also don't want to roll off the table halfway.
Yeah.
All right, it is 6 minutes. Another couple minutes.
Yeah, another couple of minutes.
Okay.
We are Italians, we are late. Always late.
It's the 15-minute rule.
Not for conferences, but a few minutes late is fine. Yeah, the guy from Rally sent me an email this morning saying that yeah, they had an emergency at work. I wasn't sure if we would be able to be here. I don't see him here, so. But he has to organize like a phone meeting or conference call afterwards. So it means that they are really interested, which is fine, still fun.
It's not a cop-out.
No, but I mean, the simple fact that he happily agreed to come over for a talk from Bologna, I think by itself is an indication of interest.
Well, what's his position there?
He's the responsible of this new. He's one of the R&D engineers of Magneti Marelli, and he's been named the responsible for this new cybersecurity thing that they are trying to do.
I've seen this. So Eaton, do you know Eaton? They do mostly like industrial. Well, no, that's right. Industrial vehicle controls.
Magneti Marelli?
No, Eaton. So yeah, I met one of the guys there he's like the R&D guy who has been tasked as responsible for cybersecurity, and he's like, yeah, man, I'm like a motor engineer. I don't know anything. It's like they gave me a promotion to be the director of cybersecurity engineering, and I have no idea what I'm doing. But at least he admitted it. That's good. It means they like you or something.
Huh?
It means they like you or something.
Completely and unbelievably, yes. It's Andrea in the first line over there. Andrea Palanca, the guy you had teleconferences with.
Oh yeah. In the blue? Yeah. He might be bored.
Huh?
He might be bored.
But he's probably here just because
That would make sense. All right.
Okay, so we can probably start if you want to take your seats. So, good afternoon, everyone, and welcome to this automotive security seminar. It's a real pleasure for me to have as a guest Eric Evenchick. Eric is, besides being a good friend, is one of the most renowned internationally speakers on automotive security. He's an embedded systems engineer by training and by trade. He's been working briefly for Tesla. Then he's worked on his own on his own hardware designs company for a while. Worked for an automotive car maker called Faraday Future, and right now is back to working on his own for his own company. The seminar of today is meant to be an introductory overview to automotive security, so it's voluntarily toned down and simplified, but particular for some students and some of the colleagues that I see sitting around. Of course, if you have any questions, if you want to go more deeper in detail, you can ask, and I'm pretty sure you cannot put Eric into any trouble in responding to any question you may have.
Don't say that.
And with that being said, Eric, it's up to you. The floor is yours.
All right. First off, thank you. Can everyone hear me okay with this mic? It's good, no complaints? Great. So thanks for the introduction, Stefano. As Stefano said, this is sort of a more introductory topic. I wasn't quite sure where to aim the technical content, but hopefully it fits into your interests and at least gives you somewhere to start if this is a topic that interests you and you want to go do some more research. So a little bit about me. I come from Canada. I didn't want like a formal bio, so I just went with pictures. And I went to the University of Waterloo in Canada, which is an engineering-focused university in a lot of ways. And there I worked with this eco-car research group to build a few different cars. And this had nothing to do with security. It was just all about sticking parts in cars that really should not be in them. So we took a Saturn Vue, which is a not great GM vehicle, the SUV, and put a fuel cell in it and ran it on hydrogen, so that was kind of fun. And that was with UOFT, the alternative fuels team. So that was sort of my introductory to automotive, because we would have to like make the car think it still had a normal engine even though it had a fuel cell or even though it had a battery. So some of those challenges kind of carried over into reverse engineering and implementing these protocols. Done a lot of work with GM, never like actually worked for them, but through various companies I've ended up doing a lot of GM work, so I've been to a lot of the GM facilities. And as Stefano said, with Tesla as well, working on firmware updates mostly, and I live in Toronto, which looks way better than it really does in that picture. But yeah, that's where I currently reside and sort of doing freelance work in embedded systems and security. So enough about me. This is sort of the big takeaway that people who are not as technical, I like to point out, is that cars really are computers nowadays. This has sort of grown over the years from being kind of very simple computer systems, just to do fuel injection maybe, to being literally every aspect of the car controlled by some code. Why do we do this? Safety is one big reason. In order to do some of the features like airbags, which you'll find in every car today, you have computers making very, very fast calculations. Modern airbags are actually looking at the seat position, the weight of the occupant, whether or not your seatbelt is attached, and a few other factors. Then they're looking at the actual crash conditions, the acceleration of the vehicle, the various sensors. And based on all of that, they're not only deciding whether or not the airbag should fire, but how hard to fire the airbag for that particular condition, and that's all happening in real time. Some advanced features, I know Tesla has recently with the autopilot, gotten a lot of attention, but features like this obviously require more sophisticated systems. They require a lot of control over the vehicle, a lot of sensors, and a lot of computing power. But perhaps the biggest reason that cars became computers is due to emissions. And I'm not so familiar with the European regulations. In the US, they have these CAFE requirements, which basically say that if you're General Motors, across all the cars you sell, you need to hit a certain target for emissions. So you can only sell big SUVs, and trucks, which are very, very popular in the States, if you can also have some really efficient vehicles that produce less tailpipe emissions and use less gas. So they started coming up with a lot of tricks that actually reduce the performance of your car in some ways, but get better emissions. Things like exhaust gas recirculation on diesels, things like diesel particulate filters and urea injection, catalytic converters even. These are all really just to reduce emissions and in some cases to get better fuel economy. So that's why we've seen kind of computers creep into vehicles. The emissions part is one that most consumers just don't personally care about at all. Some people want to save the environment and all that, but most people don't want to pay money for a car that creates less NOx. It's unfortunate, but that's why a lot of this happens. But cars are also networks, because in a modern vehicle, a complex vehicle, you can have 100 different electronic control units, which are called ECUs in the industry, and I'll use this term a whole bunch. An ECU is really any controller that's going to have typically a microcontroller inside with a bunch of I/O and sometimes some special peripherals. It's a piece of hardware, it's a box. And it's running some algorithms on it and looking at some inputs, making some decisions, and actuating anything from an engine to your steering wheel to your airbags, brakes, doors. And one thing to realize about these networks is that they're very much trusted. So you have all these components that are connected together, and they're just assuming that everyone who's on that network should be on that network, that all the things that are sent on that network are, what is expected and what was originally intended, and that once you get rid of that assumption, a lot of things break, is really the theme of this presentation. But the CAN bus in a car, this is a simple diagram of it. Basically, you have all these different controllers: suspension, ABS, instrument panel, air conditioning, and they're all going to be connected onto a bus. CAN is, I'll get a little technical for this audience because I see some faces from the lab there. CAN is a multi-master system that's fully broadcast, so every message that's sent is just sent out to everybody, and anyone can send any message. There's no routing that happens. It's just, you can do whatever you want. In modern vehicles, there's usually multiple of these CAN buses, sometimes up to like 8 of them. And they are sometimes separate but allow gatewaying from one bus to another through different components, different ECUs. So suddenly this gets to be like a really complicated network inside of your vehicle. And in the past, we trusted everything, so we don't need to worry about network security if we trust everyone on the network, but that's sort of breaking down. And now they have internet, which is exciting. This started in 1996. GM was one of the first few people to do it. They launched this OnStar thing, which lets you, call for help. It lets you disable your vehicle if it's stolen, a few other things. But today, now many cars have apps for your vehicle. They have remote control functionality. They have monitoring that the actual company that makes the car can be looking into your vehicle and seeing if there's any issues. And an interesting one is in April 2018, every car sold in the EU has to have eCall. eCall is for emergency calling, so if you crash the vehicle, airbag deployment happens, that car can phone the authorities and say it's been crashed. They're also required to provide a voice line and a set of data. So what this basically tells you is there's going to be a modem of some sort in every car sold in the EU in a couple years. So now it's starting to, it started with the expensive cars, and now it's slowly trickling into every single vehicle is going to have a cellular modem, or you won't be able to sell it on this continent, which is interesting because there's been a lot of attacks on those systems that we'll look at. Now, just from looking at a system and saying, what's the likelihood of this being vulnerable? There's millions and millions of lines of code in a vehicle. It's actually usually really hard to count them, because you'll have situations where, let's say, Fiat is buying a component from, let's say, Bosch, and they are actually buying some other things from some other suppliers, and you end up with this tiered supply chain. So there's software that's getting bought and then put into more software and then put into more software and eventually released. And in fact, most of the real algorithms that are written by the OEMs, so people who actually have their names on the cars, Volkswagen, Mercedes, people like that, it's actually done in what's called model-based design. And this is a graphical programming language, kind of like if you ever played with Lego Mindstorms as a kid. That's sort of how your car is programmed. It's part of MATLAB. They use Simulink in particular, if you're familiar with Simulink, and they use that to build code. That code then gets wrapped up in a bunch of libraries from suppliers, which gets wrapped up in a hardware abstraction package from suppliers, which eventually gets loaded on. So huge levels of complexity here. And of course, as I'll keep pointing out, this internal network is trusted, or was. So you have this really high potential for abuse. A lot of code that no one thinks that you need to worry about. And once you break those assumptions, things start falling pretty fast. So the format that I'm going to take for most of this is to kind of give you a history of the car hacking world and just sort of walk through some different things that have happened and why they're maybe significant, and explaining along the way. So these are some important events, in my opinion. 1991, we see onboard diagnostics, or OBD, introduced by the California Air Resources Board. So every car sold in California requires to implement this protocol for diagnostics. Why? Because they want to do testing in order to make sure that the emissions of your vehicle are within a certain specification, and to do that they need some data. So that was sort of the beginning of publicly accessible information on these diagnostic protocols. 1996, all US vehicles require OBD2, which is just the next version of OBD. This leads to a port being located in pretty much every vehicle sold that will allow you to connect to various networks. 2008, all vehicles sold in the US must use CAN bus for diagnostics. This is really when you see CAN, or controller area network, become like the de facto standard for every car. In 2010, we see some security research. CAESS, which is it's a research group between the University of San Diego or University of California, San Diego, and University of Washington. They published their first paper on these sorts of topics, and they actually do a lot of really good research to show that, a lot of the assumptions that these folks have made are not so great. But the one that got a lot of attention was last year when Charlie Miller and Chris Valasek at Black Hat and DEF CON released their attacks on the Fiat Chrysler. It was a Jeep that they actually attacked. So that allowed them to remotely do things to vehicles. And a lot of people paid attention just because there was this remote aspect. You could be sitting, across the world and potentially do this. And another interesting one that didn't really get much publicity was the Megamos crypto attack, which kind of leads into the whole category of attacks on key fobs and keys to get into vehicles. So we'll talk about all these things briefly and just kind of give that background. OBD2 is an interesting thing if you're playing with cars at all. It's a diagnostic standard. It lets you read some parameters. It lets you clear fault codes and read fault codes. And that's about it. There's some extended functionality that pretty much nobody allows you to use. It was originally meant for smog testing, but it provides easy network access. On most vehicles, many vehicles, you can get directly to the engine through this port, which is quite fun. Some manufacturers, GM is one of them, provide every single CAN bus on this connector, so it makes your life easy. Rather than looking for them, they're just there. And as of 2008, these were all using CAN. Before that, there was like 5 protocols you could choose from, and now it's all CAN. OBD2, if you own a car, you might want to buy one of the really cheap tools that lets you, see your fault codes, clear them, read data. They cost like, in Canadian dollars, they cost like $10, so like €6 maybe. And they're quite handy. But the CAN bus itself, whenever these all switched over to it, made it a lot easier for us to kind of look at the whole system. So CAN stands for Controller Area Network, and the reason it exists is because we have low-cost, tightly integrated hardware controllers that are right on microcontrollers. So you can buy a micro for like, they have some that are under $1 in volume now that will implement CAN. And with something like that, you can suddenly stick it on a network. Ethernet, on the other hand, you need a PHY, you need a MAC, you need magnetics. CAN, all you need is that controller, a really cheap transceiver, and 2 pieces of wire twisted together. That's the entire requirement. So it became very popular, started in 1991, and since then has sort of taken over, 89 for CAN. Since then it's taken over the entire networking for vehicles up until recently. There's a few different types. There's high-speed CAN, which is a differential signal, much like RS-485. Low-speed CAN is just a cheaper way to do it. You just cut one wire, you don't use it, and you use the chassis ground of the car. Fault-tolerant CAN is dual wire, but if you cut one of them while it's running, it will switch over to being single wire. And the new thing is CAN-FD, which allows for larger payloads and faster bit rates, but it's not really used in any vehicles today. And a typical CAN bus, again, might look like this. So you have a high-speed differential bus with the important things like engine control, body control, transmission control, anti-lock brakes, and then that will act as a gateway to actually send messages through to less important things that are maybe running on a cheaper single wire CAN bus like door control modules that let windows go up and down, instrument panel showing you data. So it really just depends on the particular application, and a lot of it also depends on making the harnesses in the car, the actual physical wiring, as cheap as possible. That's a huge cost. So to show how CAN works really simply, the typical way that CAN would work is you have just a bunch of data being sent out, and or a bunch of frames. Each frame really consists of an ID and some data bytes. CAN is really simple because I can show it in one slide, and unlike Ethernet. But really all it is an ID, which is 11 bits long, so 0 to 7FF hex, and then 8 bytes of data. And that's pretty much all you can send. There are a few other modes. There's things like remote requests. There's extended IDs that allow you to use 29 bits, but the vast majority of what you see in today's vehicles is just this. And on the hardware side, there's a little bit more magic. It does some acknowledgments. It has a CRC that's built in, so you know that the bytes that you're getting are correct. But really all it is an ID and 8 bytes. So typically you'll have something like an engine control module sending out these frames at a periodic interval. So maybe every 100 milliseconds it's sending this message out. And everyone else in the bus is free to receive those and look at them and do something with them or throw them away. And in a really simple example, you might have a message that's going out of the engine control module, being received by your instrument cluster, which is your speedometer or tachometer in front of the driver. And some bytes in this will have a meaning. This is defined by the people who engineered the car, and it's kind of done by a few rules, but mostly just to reduce the number of messages you need. So in this kind of contrived example, unfortunately the layouts that I do have are all are confidential, so I have to make up examples for this. But you might have something like OX5DC and a database file, which is just it's actually an ASCII-based file that shows you the whole layout. We'll tell you that means RPM, engine RPM, and you'll do a quick conversion. That database file might tell you to multiply it by something or add something, but then you get to a real engineering unit value that goes into the controller, and now your instrument cluster can display 1500 on your tachometer. So it's really simple messaging. You just shoot out messages and people listen for them and take action. So one of the easiest attacks that you can do on CAN is just injecting messages. Because it's trusted, and because all the traffic is visible to all the controllers, and any controller can really send any message, you can just shoot out messages faster than anybody else does. So an example here might be that a rogue controller, which could either be you attaching intentionally some device, or maybe you've got a remote exploit on a head unit that's connected to the internet, and now you're able to send CAN frames. And this has happened in real life. Now you can send whatever you would like. And this particular example, we just replace these 2 bytes. The instrument cluster receives this, and you get a car that's sitting still but has its tach at 8,000 RPM. Now this doesn't work perfectly all the time because you're fighting against other controllers that may be sending their own correct messages. So you need to sort of flood things, and sometimes there's validity bits to make sure to say, is this signal valid, and you need to change them. But you can really easily just do this sort of injection to modify certain operational parameters of the vehicle. So that's sort of the real quick introduction to why CAN is trusted and why you can usually mess with the bus once you're on it. But there's advanced diagnostics, which are sort of the more cool protocol things. So the ISO 14229 standard is called Unified Diagnostic Services. It defines a bunch of services, but the details of how those work for a given vehicle are proprietary. So BMW, they may implement certain diagnostics features with certain codes, so saying, these routines are available to you, and GM would have a whole different set of routines available. There's a few that are standard in that document, the 14229 document, but for the most part, the fun stuff is specific to that manufacturer, which is unfortunate, but that's life. So there's a whole host of these routines. I put 3 that are kind of fun. Routine control just lets you run arbitrary routines. So things like actuate the brakes is actually one that is on most brake controllers. You can modify parameters, so you can change, in some cases you can change things like the VIN number of a controller to a different VIN number if you happen to have a controller that doesn't match the rest of yours. So for theft reasons, some of these matter as well. And then there's firmware updates. With certain controllers, you can actually totally load a new firmware onto that controller and keep it running. Well, reboot it and it will start running again. Now, these are secured sometimes. So the features that are meant to be used by mechanics, typically there's no security on them because they have to put these tools in every mechanic's hands, and let's be honest, you're not going to be able to do that without the keys slipping out. So they just don't secure those. However, the more advanced things like firmware updates, sometimes, well, usually you'll see security. Changing a VIN number, you'll see security. Changing an odometer, this was the start of automotive security in some ways, was people trying to change odometer values so they could sell their car at a lower mileage. So that's secured. I've seen some really bad security algorithms, including things like subtract a number from something, the fixed number, it sends you a value, you subtract like OX1234 and send back that, and it unlocks. That's like a real thing in a 2013 vehicle for the airbag controller. So these aren't always good. Your mileage may vary when you start to look at different manufacturers do things better, some of them do it really badly. But these are really fun to play with because they expose functionality that you were never supposed to have, so you can have a lot of fun. So quick summary of the whole CAN thing, trusted network, and once you're on it, you're going to be able to do something to the vehicle. Will you get it to behave exactly how you want it to? Maybe that'll take a lot of research, but will you be able to mess it up and make all the warning lights come on? Absolutely, that's really easy. So CAN is not really typically secured in vehicles today. But the interesting research in this has sort of shown kind of bigger vulnerabilities that are not just let's plug into CAN and send messages, but how do we actually exploit it from other vectors? The attack surface of a car started off pretty small. I mean, originally you had one computer controlling the engine and it might have a diagnostic port under the hood. Today you have Bluetooth, Wi-Fi, you have 3G connections, CDs, USB, you have media players, and the list goes on and on and on. So these folks from the AutoSec group, they back in 2010 actually showed some of the coolest exploits that have been done on cars, in my opinion. Because they figured out how to do it through CD, this media pass-through, Bluetooth, and cellular. So they could use any of these attack vectors to do this. And I think the coolest one is they could actually call the car with by using its public phone number and then play a song into the phone. And what had happened for this particular remote control functionality is they had a special, like modulated in an inaudible part of the spectrum, a way of putting data there and making vehicle requests. So they actually figured out how to get remote code execution by sticking data in a song that you couldn't hear if you were the driver. So you could play like someone's favorite song or whatever, and little do they know you're actually sending messages on the CAN bus at the same time, which is really cool. It's like movie stuff, but it actually happened. So they used these exploits to get code execution. Once they had that, this was connected to most of the car on CAN, so they could control CAN and do all the things we talked about. And in their particular example, they used some advanced diagnostics that were specific to this manufacturer to really control the vehicle. And if you're wondering what they could do, this is their table from their paper. I mean, probably the most fun one of these is the last one, which is forces wipers off and shoots windshield fluid continuously. That just sounds like fun, but you can control the horn frequency, permanently activate the horn so it will never turn off. It's, you know, some of these are more serious, some of these are funny, but these are all things that they actually did test, some of them on a runway at speed. And all of this was doable by calling the car and playing a special song. So yeah, I think that's a pretty neat set of exploits. Miller and Valasek made a lot of news last year with their attack, and it's just sort of worth looking at because it's a very good example of how the industry sort of broke down in terms of auditing their own devices. So really what happened was there was a Harman head unit on this vehicle. Fortunately, all the manufacturers are public for this particular attack, so I can use their names. Harman made the head unit, which does all your radio features, connects to the internet, and acts as your sort of infotainment system, as it's called in that industry. And it was running Linux, and it used dbus. Dbus is like an inter-process communication mechanism for Linux. If you use Ubuntu, you have dbus. It allowed dbus on Wi-Fi and cellular through an open port. And it allowed anonymous authentication, so you didn't need a password. You could connect to dbus, and then you could do IPC calls on that system. So you could tell to do stuff. And there's a ton of work that went into actually going from that to being able to take over everything. But what it really came down to is they used this Linux system, which had been, in the words of the folks at Fiat Chrysler, air-gapped from the actual CAN bus. They used it to update the software on the other side of that air gap because it was actually connected to a microcontroller that was connected to CAN. So Linux wasn't on CAN, but Linux was connected to a V850 microcontroller, which was connected to CAN. And they just changed the code on that V850, and once they were able to run code on there, they had full control over CAN. So this is an example of a security mechanism they put that looked like, hey, this is pretty good. I mean, the Linux system, if it's compromised, you can't do anything because it can't communicate with the vehicle. That was true, except you could do firmware updates, and there was no code signing. So you could just write your own exploited version of the firmware, stick it on there, and have the rest is kind of history, I guess. This paper, along with the other one, they're very interesting reads if you're into this stuff. But one thing to note about this is nobody really knew who to blame, because Fiat Chrysler, they specified a secure system, and Harman implemented it to their specifications. Nobody said that this dbus port shouldn't be open, and nobody said that anonymous authentication shouldn't be allowed. And unfortunately, that's just how the automotive industry really works, is you make specifications and you say this shall do this, shall do this. You have to kind of enumerate everything you want. And the job of the people building that, in this case Harman, is to build exactly what you want at the lowest cost possible to them, and then sell it off to you. And security doesn't really work that way, right? You can't specify, this system should be secure and have that work. You really need to look at the system in a lot more detail than just a specifications document. And this is something where, if anyone had done penetration testing on this device, they likely would have found the open port, and you wouldn't even have to go into this detail. You'd say, why is this port open? We don't know. It was for testing. Oh, well, you should close it before we go to production. Great, and that's solved. If they actually had to leave it open, you go one step further and you say, well, how do you authenticate to it? And then we get into, oh, well, it's anonymous. That's not good. But none of this really got done because it wasn't a thing that either of them were doing. So according to both parties, their system was secure or met the spec, but it obviously fell apart whenever you actually put it together. The Megamost crypto is an interesting one, just because it lets you steal cars, which might be of interest to people. Basically, it's an immobilizer. The way that these work is they prevent hot wiring. No longer can you just connect the red wire to the blue wire in the movies, and have the engine turn over. There's some secure hardware that's going to do a handshake, and that actually will enable the engine controller, or allow the engine controller to start the engine. So immobilizer is really simple. They detect a valid key, often using things like RFID. And if you compromise an immobilizer, you can typically just hotwire the car. Megamost was one that was used by a lot of people, at the very least by Audi, Fiat, Honda, Volkswagen, and Volvo. So that's millions of cars. And it was used for quite a number of years too. Volkswagen actually took these guys to court, the researchers to court, because they wanted to protect the release of this information. And they delayed it by 2 years, and it finally was released, but the slides are interesting to look at because they're like, we can't take any questions. We hope you understand. Our lawyers have told us that we're allowed to present only this. But basically, it was an attack that really was an attack on the crypto being used by these MegaMost devices that would allow them to be sort of simulated, and you could kind of, as they call it, wirelessly lockpick a car. Now, this was sort of one of the really complicated attacks on these key fobs or immobilizers. There's a lot of more basic ones that are actually being used in the wild. Roll jam is one that was demonstrated at Black Hat. Very simply, it jams the valid signal from a key whenever you hit the unlock button. And you're wondering, well, my car isn't unlocking, that's weird. You put the key in and turn it maybe, or if you're locking, it just doesn't lock and you don't notice. But it's actually jammed this rolling code. So the actual cryptographic key will change every time you hit the button. But what this has done is stopped it from actually being received. So you have a copy of the next key, but the vehicle hasn't received it yet. So all you need to do now is replay that thing you received, and the vehicle that thinks it's valid, it hasn't received the key yet, but it's valid. So you can unlock the vehicle that way. And this is actually a pretty common attack. It's starting to be not as possible because the keys are getting better, but it was really common on both garage door openers and on cars. If you look at key lock, it's one of the chips that was actually super vulnerable to this. And then range extension is a really simple attack that works quite well. Basically, you just either amplify or relay the signal from a key. So someone has the real valid key in this classroom. Someone sitting beside you has a device that's going to either amplify that or send it to another device. And your car outside, now someone near it can just pretend like they have the key and get in it. One kind of strange thing is that you figure, well, once you drove away, this wouldn't work anymore because you're no longer within range. Most cars, they don't want to shut down if they lose the key for safety reasons. It's not very safe for your car to just turn off in the middle of the freeway, or they don't like that from a safety standpoint. So the car will just keep running, and usually until you stop and shift into park. If you've ever forgotten your key and started the car and forgotten the key, you may have, and I know some people who have ended up stranded because they didn't realize they didn't have their key. They drove 100 kilometers, then put the car in park, it shut down, and they couldn't start it again. So it does happen. So these are two really kind of trivial attacks that actually do work, and there is proof that they're being used in the wild. The other topic, and really what I've been working on a lot, is more the tools for doing this. And whenever you don't have access to tools, it becomes pretty hard to do these attacks. We see that CAN has existed since 1989, but no one really looked at it until 2010. Well, why is that? For a long time, the tools were very expensive. Vector, who are a German company that make a lot of this stuff, their hardware is in the five figures. You're looking at least 10,000 just before you have something, plus software licensing, and some of their stuff needs training, and you're not going to get it if you're just doing some research. Cavassor is another one that's been around for a while. Their tools are mostly focused on logging, and they're also still a few $1,000s typically. More recently, we saw Peak and Grid Connect. It's the same device. It's this little white box. It's a few $100s, which is much better. Still a little pricey, and their software is kind of closed down. They have an API, but it's really not fun to work with. And the ECOM cable, which is actually what Chris and Charlie used on that Jeep for a lot of their CAN-based attacks when they were doing the research. It's a device, I haven't actually used it, but it's a couple $100. It's a nice cheap one. Moving down the cost list, though, there's a few open source ones, one of which I'll talk about. Goodthopter was one of the early ones, and if you've used the GoodFET, I don't know if anyone has seen Travis Goodspeed's GoodFET. It's like a SPI UART I2C JTAG device that's just like a little tiny PCB. A guy by the name of Andrew Reiter, he built a CAN version of that called the Goodthopter, and that was available for a little while, but nowadays if you want one, you have to order PCBs and like build it yourself at home on a toaster or in a toaster oven or however you prefer to build your hardware. The OBDuino is a similar thing. It was an Arduino that would work with OBD and could be used for doing some displays, but it was really a open source hardware thing that you could never really took off. You couldn't buy it. I got a little bit annoyed by this because there was no open hardware, so I built this CAN-TAC device, which is really simple. It's a USB to CAN, and it works with Linux, some utilities on Linux that I'll show some pictures of. But the real theme there was I just wanted to get something out there that was actually kind of usable out of the box. And the other thing that you can buy, and these are super cheap, and look at the Amazon reviews before you buy them because some of them are really sketchy. But the ELM 327 knockoffs, which ELM 327 is a chip for the OBD protocol. There's a bunch of knockoffs of these, and mostly made in China. You can buy these devices that will do either over USB or Bluetooth. Pretty much all the OBD stuff, not too much more. They're very useful if you happen to own a car and want to know why your check engine light is on, or if you own a car and would like to turn that annoying light off. For probably about 10, 15 euro, you can buy one of these things and forever use it on any vehicle until OBD2 goes away. You'll save your friends some money if they believe that you actually know what you're doing, but sometimes they don't and end up going to the mechanic and then they actually get the same thing done. So I've had that happen a few times. So yeah, the OBD2 tools, these are some examples of them, and the annoying check engine lights. Anything past 1996, these will work with. There's Android apps, like Torque is a really nice one. You can just drag in graphs and it will plot like your mass airflow or your vehicle speed or whatever you'd like. Some are cheap and of questionable quality. Your mileage may vary. Don't blame me if you buy the €1 one and it sets your car on fire. I've heard a few nightmare stories of the really cheap ones. So the CAN-TAC device, there was nothing readily available. I wanted something open source, open hardware. So yeah, CAN-TAC, it's one channel CAN to USB. It's got the standard DB9 connector on one end, which is used for CAN a lot, and USB-B on the other end, because I've broken so many micro USB connectors in my life, I just couldn't bear to put one on there. It also has jumpers for selecting the pinout. There's different pinouts for different cables. There's two common ones, so it lets you switch between them. And what you can do with this is plug an OBD to DB9 cable in, and that goes straight into a vehicle, so it's like really fast. Just plug it in and hit go, and you just start seeing all the CAN frames. One cool thing about open source hardware is people can fork it. One that I like to note is the Cannibal device, which is the other one up here, by a guy named Ethan Zonka. He built this because he was building something and he wanted to like embed it in his project, so it's like really tiny. It's micro USB, and it goes out to terminal jacks. So two things that do CAN. And what they'll allow you to do is send and receive raw CAN frames. So the OBD2 stuff, it's mostly useful for the diagnostic protocols, specifically the OBD ones. This will let you look at all the frames. It will let you send any frame with any data. And it will work on all vehicles, really 2008 and newer, with some exceptions for older vehicles. There's some charts online that show what does CAN. So the hardware is nice, but without software, it's kind of useless. There's two real options you can do. The first one is what I started with for this project, and then there's a new app that I've been working on. So on the Linux side, you can use Wireshark, which most people don't expect Wireshark to do CAN, but hey, it does it. There's something called Socket CAN on Linux, which basically is a hack to allow a CAN device to look just like an Ethernet card. So you actually get like, instead of ETH0, you get CAN 0. And then you like IF config, CAN 0 up, and then Wireshark can connect to it. And it will start like spewing out the messages. It's quite nice. You can log things. You can look at all the different parts of the frame. Everything you'd expect with an IP packet, but with CAN. And so that's pretty useful just because everyone has or knows Wireshark if they work in this sort of stuff typically. It's easy to get started. The real limitation of Wireshark, of course, is you can't send any frames, which makes it only half useful. So I've worked on a new application, which I have a pretty bad screenshot of here. But this is just an application called Contact app that lets you connect to the device, view all the frames that are going by, send frames. It also has a live view, which is what I call it, where it will show you all of the CAN frames by ID, and instead of just spewing a big list of them, it will actually update the data and show you which bytes are changing. This is essentially how you reverse engineer CAN buses, is you sit in the car, you plug in, you look at the data, and then you start doing things and you watch what changes. So a friend of mine wanted to know where the GPS coordinates of his car were on the CAN bus. So we got in his car and we started driving around, and we were like, okay, GPS, it's probably gonna have a slow rate. It's gonna be sent maybe every second, right? And sure enough, there's some 1-second messages. And we start driving in a more or less north direction, and one of the numbers changes more than the other, and you do some math and it resolves to the GPS coordinates. So some things are really easy. GPS was actually one of the harder ones. Pedal positions are super easy. You just start pushing the pedals and watch what changes. And this is sort of the first step in understanding what's on a CAN bus, is this, watch the CAN bus, do something, see what changes. Like really, really elementary reverse engineering techniques, but they work like for most of the things. And now it also has features for doing diagnostics, not just OBD, but the UDS stuff. Not all the services yet, but the idea there is there's not too many tools that let you do that. In fact, there's just about nothing that's free that lets you do that. And those are more advanced protocols, and as we know, the more advanced a protocol gets, typically the more issues there are with it. So those are fun things to look at as well. So yeah, I'm just kind of getting to my summary, which is, why is this stuff not so great? What are the challenges? Like, nothing here is particularly technical in, there's no really fancy exploits or anything. I'm really just connecting to a car and sending stuff, and the fancier exploits are, taking over a controller, then connecting to the car and sending stuff. Really what it is we're seeing more features in cars, we're seeing more automation in cars, we're seeing more connectivity in cars, and as those things kind of go together, it gets a little scary, because now you have remote attacks that are possible due to the connectivity. The potential for an attack, the actual damage potential, goes up because there's more automation. If you can control steering, that's way worse than honking the horn. And there's more features. Just in general, there's more lines of code, and there's more that could go wrong. Again, the example of being able to play a song and take over a controller, that was a feature that allowed them to remotely access the car when it was outside of cellular data and only had cellular voice. So that's what let it happen. There's the supply chain problem, which if you end up working in the automotive industry is something you'll deal with a lot. You have the OEMs who make the cars. You have the tier 1 suppliers that make parts that go in the cars. You have tier 2 suppliers that make the parts that the tier 1 suppliers use to put in. And there's this whole chain of manufacturers. And the who's responsible part, really just look at the Jeep incident, where we spec'd it this way, they built it that way, but it's not secure. And what we're starting to talk about in the industry now, and there's some interest in, is yes, we should be doing things like penetration testing on these devices before we put them in cars. It probably makes sense, especially as we start to see them really become computers. All the things that you would expect from a web application really are going to start applying to cars. And the last one that's quite interesting is, how do we patch cars? This is something that Tesla probably were the first people to be able to do it widespread and to pretty much all the controllers in the car, which was pretty cool. We could update code on everything from like the center display with all the infotainment features, all the way down to being able to update the code on the door handles in the car, which is actually something I worked on. It was an interesting challenge to make the door handles load new code. But in other cases, it's not so easy. With Jeep, they had to send out USB sticks. And that obviously is another potential for attack if people are sticking USB sticks in their car that can load firmware. Like, what if you send out your own USB sticks to people and say, plug this in? It's not quite clear. I mean, a lot of OEMs are working on getting to the point where more things are updatable, but it's not an easy problem. A lot of these parts of the car, a lot of these ECUs, they're built to be cheap. So you're looking to have as little memory as possible. You're looking to have as little computational resources as possible. You can't do really good crypto on them. You can't store extra application just for doing certain security features and justify it to the business side saying, well, we want to make it more secure, so this part's going to cost an extra $1. And that's sort of where we're at with the industry right now, is this bit of a fight back and forth between the engineering side, who really know the issues are there and they really want to fix them. And then there's the business side, which is, well, until this is really a problem, there's no business cost to not fixing them. So we need to prove that there is a purpose of doing it, and it's a struggle back and forth. And yeah, that's not unique to the automotive industry, I don't think. That's, if you're working in security, expect to spend a lot of time trying to nicely convince people that security is actually important. It's unfortunate, but true. So I know that there are some people who basically their entire jobs is just convincing management type people, explaining security to them in a way that they can understand and convincing them that they should spend money on it and do something about it. But at the end of the day, it comes down to sort of a cost-benefit analysis, and we're not quite there yet, but we're starting to see the concern, and slowly I think it will start to flip over, especially as we see things like self-driving cars. The damage potential suddenly just got massive. You may end up in a situation where we just can't have self-driving cars unless there's more security, and that would really make people pay attention. So that's my kind of presentation material here. Here I have, well, we can do as many questions until we run out of time or you get bored. I'm not sure how much time we have. If you want to email me or Twitter me, that's possible. And links to everything that I linked to elsewhere, if you want to take one picture and look at it later or whatever. I can probably give these slides to Stefano if people actually want them after. But yeah, we can just do questions, but they're recording, so they want you to use the microphone. That's my only thing I've been told to say. But yeah.
So if there are questions, can I ask you to carry around the microphone to the class? Thanks. Questions? Well, first of all, we can actually thank the speaker for his talk. There's a question over there.
Actually managed to stay here for some more time. So I'm from the industry side, and one of the critical aspects is actually testing for security. If you make a component or if you make a subsystem, then you have the problem of somehow proving that it is as secure as possible. Can you say something about that?
Yeah, so I think a lot of the testing on the embedded side is similar in how you lay it out to what you'd see with really anything else. You're looking at attack surface. What can people put into your device? How can they, modify its operation? If you're looking at a head unit, like I said, you got Bluetooth, Wi-Fi, and all this stuff. In the case of something that's just a wired network, someone can maybe connect to that, but is that likely? You have to do the analysis. So the threat modeling part of it really is what comes in, actually figuring out the potential attack vectors, and then based on that, the likelihood of compromise through them or any possible exploits. Another important thing that I've seen, another important thing to look at based on what I've seen is what assumptions have been made about that device. So with cars, the assumption is that if you're inside of someone's car, you are authorized to use that car, and you're trusted. And that is sort of true, but I hear Milan has a very popular car sharing program now. You might not necessarily trust everybody who is in the car before you or even know who they are. So that's the other side is, what assumptions are you making about the security model of your device? And also, how can people get in are sort of two of the initial things that we typically look at. And from there, a lot of it comes down to knowing more about what the particular system is. And with a car, it's obvious taking over an engine is bad, taking over brakes is bad. But for some other systems, it's not entirely clear what the damage potentials are. And again, it does often come to business values. So what side do we need to protect that's going to be of interest to your corporation? Are they worried about intellectual property leaving a device? Are they worried about someone remotely controlling the device? It really comes down to the particular situation.
Any other questions? Actually, I have a follow-up question on that, and because it seems to me that obviously, in the broadest possible sense, testing for the attack surface makes sense, of course. But it seems to me that if you want to test for the security of the device, some way you should have the specification of what that device should do in the security, or what guarantees it should give in the security area. And I remember you commenting about kind of a debate between OEM and Tier 1 about who should impose security constraints upon whom. Do you want to comment a little bit on that?
Well, that is a bit of a debate, yes. Who should actually be specifying it? One of the challenges there is that specifying security is not, you'll never get it totally right. I mean, it's this, you're dealing with this game where you have to do everything perfectly, and if you do one thing wrong, you lose. So, and I've seen some frustration from some folks in the industry about that feeling that, they have to do everything right or else the whole thing was for nothing. So one thing that actually brings me to is the importance of patching and being able to update these systems in a secure manner. It's really, the patch cycle for that MegaMouse crypto thing is literally replace all of that hardware, everyone's keys and the receivers in the vehicle. It's not feasible. When you're talking about software, and as things move more and more to software, it is feasible to come up with systems to update them. And so I think that is another side of it to sort of get around the not absolute specifications of security, because there's no such thing as a perfectly secure system, and especially when you're dealing with the constraints of money, time, and resources on an embedded system, it's probably not going to be ideal. But you're right that the specifications are important to look at. Sometimes you can look at a product design, and if you're familiar with the protocols, you can immediately go, oh, well, this is broken because they're using Bluetooth like this, and Bluetooth can't do that securely. I mean, there's no way to do that right. So that's the other side of it, is actually just looking at how they're implementing it. And once you've dealt with a few different systems, it starts to become pretty obvious that you see the same mistakes happen over and over.
Okay, any other questions, comments, remarks? Seriously? Okay, fair enough. So let's thank our speaker once again.
Thanks for coming, and hopefully this, if you were interested in automotive stuff, gave you sort of a background of where to look. If you have any questions after this that I know you don't want to get on recorded or whatever, let me know. I'm happy to answer those.
Thank you very much for coming.